I thought you were talking to me for a minute. No. All right. Go ahead. No? Okay. So a statistic is a number computed from a sample. A parameter is a number computed from a population. We use a statistic to estimate a parameter. If we're working with proportions, our statistic is p hat, and our parameter is p. If we're working with means, we use x bar for the statistic and mu for the parameter. So today we're going to look at sampling distributions and population distributions. And I'm going to try and talk over his videos. They're driving me insane. It's daily. It didn't used to be daily, and now it's daily. All right. We're going to toss, well, but, do I want to give you the coins? Let's answer a couple questions before I give you guys the coins, and then we're going to toss some coins. So I'm going to give you a coin. Excuse me. We're going to toss it 20 times. And we're going to I almost said reward. We're going to record the proportion of heads we get. So proportion, we use fractions and decimals for. So it's going to be out of 20. And then the number on top will be the number of heads you get when you toss it 20 times. So when we're looking at a sample of coin tosses, we're going to be looking at a sample of size 20. What is the population here? And every year, this one kind of stumps kids because it's kind of weird to think about. If I'm taking a sample of coin tosses, today is just not my day. Coin tosses. Our population is all coin tosses ever.
Yes.
Everybody goes, what? And Zach goes, yes. I like that, Zach. So, a population, remember, is when you're looking at everything for that variable. Well, coin tosses, we don't know how many have been done in the last 10 years. We don't know how many have been done ever. So we just get to kind of generalize and say it's all the coin tosses that have ever been done ever. So the parameter that we're looking at, we're recording the proportion of heads. So the parameter that we're searching for is the proportion of heads. And we know that with fair coins, the proportion of heads should be what? Say that again? 10 out of 20 or 0.5, right? We should get it about 50% of the time, 0.5. So P, our parameter for proportion, should be 0.5 because coins are supposed to be made that it's equally likely to get heads and tails. So, like I said, we're going to take a sample. Our sample is going to be the 20 coin tosses. And when you guys record your proportion, because it's coming from your sample, we're going to use the notation for the statistic of a proportion, and you're going to figure out p hat is however many heads out of 20. So now I'm going to bring you a coin, unless you have one, but I've learned in the last few years, kids don't have coins like they used to. Toss it 20 times, keep track of how many heads you get. Somebody has. You don't have one? You're just getting them. Either.
I get 3.
No, hand them back.
Oh. I'd be 3 cents richer.
Don't lose my pennies. Hand them back. Do they give them back? Zach, hand them back.
Oh.
Did you think I was joking when I said
My bad.
I had it in my hand.
I forgot there are other people behind me.
There are other people behind you. She's not here.
She's not here? Okay.
Thank you. 13,
Whoa. Oh my god, I've done 3. I just like your I got 8 out of 20. Oh, also.
Yeah.
I thought you said 8 out. Today is not my day. My brain is just struggling. Like, I just now remember that alien. Alright. Sounds like the coin tosses are slowing down.
I got 10 out of 20.
Eric's over there doing them super official. Like actually flipping them. I just tossed my coin on my paper. He's really doing the whole. I can't do it that way. It just doesn't work. He can flip it to the ceiling. Are you done, Eric?
Yes.
Okay. All right. So down here at the bottom, I think it was dangerous to hand out coins. I didn't realize it'd be quite so distracting. Down here, you should have your proportion. So when I did mine, I got 8 heads out of my 20 tosses. Now, proportions we tend to use decimals for. We can write them as fractions, but like in your textbook, if you look, they're all in decimal form. So 8 out of 20, if we multiply by 5, right, we would get out of 100. So it's 0.4. Sorry, I'm not trusting my brain today with everything else that's going on. So I got 0.4. You guys should put your decimal. And I'm going to go around and ask you for your proportion. I want it as a decimal, please. Okay? And we're going to record them. Yes, you should record everybody's as well. Okay? So down here, it says record the values of your classmates. I'll ask everybody for theirs, and we'll write them down together. So, Eric, you get to get... What was your proportion of heads? 0.6? Okay, thank you. Noah?
Wait, are we rounding?
There is no rounding necessary. It's either going to be a 0.6 or a 0.4, or it's going to end in a 5 because it's out of 20. What'd you get, Noah? 0.4. 0.4. Hayden? Calvin?
0.55.
Amelia? Shelly? Zach?
0.5.
Hannah? Michelle? Hannah? What'd you get? I like how you said Anna O.
I thought you said Hannah.
Oh, no. I could see that. Sorry. Haley? Thank you.
Yes.
Maddie? Cheyenne? Molly? Jillian? Tyler?
0.45.
And Nate. What?
4.5.
Oh, the 0 threw me off, and then my brain put it, you said 0.45. Sorry. And then we're going to add mine because I want to feel like part of the group too. So we're going to put 0.4 there. So we're going to make a sampling distribution below, which is just a fancy way to say we're going to make a graph of our data. Now, I've taught you multiple graphs, histograms, box plots, dot plots, scatter plots, stem plots. I feel like I'm missing one for some reason. Which one would you guys choose for this? Stem? Who said dot? I like dot too. You could do a stem. I just personally, stem plots, you can see the shape, but I like dot plots to see the shape the best. Sorry. So I'm going with Hannah. Sorry, Calvin. No offense to you. I like the dot plot. Eric, you stay out of this. So to make our dot plot, we're going to draw a number line, and then we're going to put dots above it. So our lowest was 0.35, highest was 0.7. So why don't I go, let's go 0.3 to 0.7. 0.3, 0.7, which means 0.5 is right in the middle. So then I have 0.4 there, 0.6 about there, and then 0.35, 0.45, excuse me, 0.55, and 0.65. And then we're just going to put our dots above them. We all have the same set of data, so in the end our graphs should look alike, but I'll let you guys make your dot plot. I'm not going to read all the numbers out loud to you. What are they watching over there? Who knows?
I always hear that, like,
At the end of last period, he was playing music. Sounded like they were just having a dance party. Made me feel like I need to make my lessons more exciting.
So we're eating.
Tomorrow we get to play with Reese's Pieces.
You not eat them?
Can you eat those?
Yeah.
Reese's Pieces tomorrow, not Starburst.
Can we eat them?
And then, yes. And then the next one we're gonna, anybody got a peanut allergy while I'm saying that? Okay. And then after that, the next candy we get to play with is Hershey Kisses. That's at the beginning of chapter 8.
Man.
Anywho, we now get into the, in my head, the fun part of statistics where we start playing with candy.
Yes.
We'll play with Skittles later in the year. Lots of fun stuff. All right, so hopefully you have your dot plot done. This graph is the sampling distribution of p hat. So down below, question F. Does the sampling distribution display bias? What does bias mean again? What does that mean? Consistently underestimating or overestimating the parameter? Thanks. All right, so bias, just in case you forgot, that means that we over or underestimate what we're trying to measure. So up in the square above, underestimate. I don't know why that just doesn't look right. Probably because I didn't put a space between under and estimate. Up here, oops, sorry. We talked about the parameter being 0.5. There's 1, 2, 3, 6, 9, 13, 15, 17. I make 18. So there's 18 dots. So our center is going to be the 9th and 10th dot. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one and this one. So where is our center of our sampling distribution? How do we find the center given that one is here and one's there, Cheyenne? And if we add 0.45 and 0.5 together and divide by 2, we get right in the middle at what? 0.475. So, knowing that the parameter we were trying to estimate is 0.5, and our sampling distribution puts the center at 0.475, we would say that our sampling distribution has low bias because we do underestimate, but we're really, really close to the actual parameter, so the bias is low. Let's see, I'll use peak. Am I off the screen? So, like I explained, it's low because our center is close to the actual parameter, but we still underestimated, so we would have bias. Question G, does the sampling distribution display high variability? So high variability, or variability, I shouldn't say high, is talking about your spread. So our highest is 0.7 and our lowest is 0.35. So that's what, 0.35, and we know that it should be centered around 0.5. So I wouldn't say high variability, but we definitely have some moderate variability because we do have quite a range between our proportions. Sorry. Variability, just remember, is spread. Tells us about the spread. So if we look at our range, 0.7 minus 0.35, we get 0.35. So I would say moderate variability. And then I made a note at the bottom, just so I'm completely honest with you guys. Our sampling distribution is not a true sampling distribution, because remember I told you last time the definition of a sampling distribution is all the possible samples of the same size, which there's no way we could look at all samples of size 20 of coin tosses ever. So it's not a true sampling distribution, but for our class it is. And remember, the definition of a sampling distribution is going to be on your test. I promise you. I will have a multiple choice question about that one. Any questions before I flip her over? Alright, so now we're going to look at some averages. So let's say we want to estimate the average number of siblings for all the AP stats students in this class. We're going to do this by selecting a sample of size 4. So what is the population on this one? I heard some whispers, but nothing where my brain could actually tell what was being said. What's the population? What are we trying to estimate? Number of siblings for AP Stat students in this hour block. So our population here is all AP Stat students in block 3. Students, excuse me. What's the parameter we want to figure out? Not just number of siblings, but the average number of siblings. And for a parameter that is an average, what notation do we use? Mu. What's our sample going to be? Sample size, I guess, is really what I should say. I heard somebody say 4. Not sure if it came from that area. We're going to look at 4 students for our sample. And when we're working with means, our statistic notation is what? Mu is the parameter. What's the statistic? X bar. So, first thing we're going to do is we're going to go through and find out how many siblings all of you have. Every year I get the question, do half siblings, step siblings count? And I'm just going to say yes. If they're a sibling, they count. Half, step, estranged. I can't think of any other things. All right, we're going to start on this side. Tyler, and you guys should be writing this down too.
I have 2.
You have 2. Oh, sorry. And you need to. Well, that's what I don't. I was going to say. It says number of siblings, so he has 2 siblings. So do we want to include ourselves or not?
No.
No, the question is not
Eric has spoken. Okay. All right. Tyler's got 2. Nate,
Or what?
how many siblings you got?
Do we count half siblings and step siblings?
We just said, I'm sorry. I wasn't paying attention.
What?
I'm sorry.
I said include half
I'm
siblings,
sorry.
step siblings, estranged siblings, but you do not include yourself.
4.
Damn.
5.
What?
Sorry.
Oh, 4.
People that I don't talk to anymore, but they're still technically my siblings.
Estranged. See? Molly, it's got 3, right? Jillian? 5. Oh, that's right. Jillian was talking about her mom having 6 kids the other day and how crazy she was. I agree with that. Anna? I'm sorry, Laura. What is this?
I was
for?
just told to give this to you.
Who told you to give it?
Mr. Haley.
Oh, tell Mr. Haley thank you.
I will.
You said 1, Anna? Okay. Haley?
2.
Maddie? I'm sorry, the door shut. 2. Cheyenne?
2.
Michelle? Hannah? Sorry. Just 1? Okay. Zach?
0.
Ooh, our first only child. Calvin?
8.
Whoa.
Oh, wait.
What?
What? Why did you say 8 then? Are they half siblings and step siblings? You're just messing with me.
I learned in Virginia one question.
And that's it. Where'd the other 6 come from? Are they figments of your imagination? Exactly. One's in Virginia, the other's in Portland. You need somebody to play with, right? The imaginary friends to the extreme, Calvin. Amelia? 1. Shelley? 2. I would hope you'd say the same number as Haley. I would hope so. Hayden? 2.
Damn.
Noah?
Okay, all the presents.
3. Eric?
4.
Can I be included?
Yeah, go for it.
I got 2 siblings. I got one in Portland and one in Washington,
Virginia.
not Virginia.
But you have 6 here.
I do have 6 imaginary siblings. Well, I suppose if you count all my in-law, brothers-in-law. I mean, Bells has 2 siblings. I've got 2. They, well, I have a sister-in-law. The other one has a girlfriend, but technically they're not married. And the same on my side. My sister's married. My brother has a girlfriend. So 6. There we go. I figured out there's 6. All right. So we're going to make a dot plot here for our number of siblings. I was like, where did my ruler go? It's right in front of your face, Amber. So lowest is 0, highest without Calvin's imaginary siblings is 5. Yeah. Not break it. I swear, every time I let a kid use one of those, they get broken. Alright. We got a 2, 5. I put too much pressure on you, Yana. 5 for 1. 1, 2, 3. 4, 1, 0, 2, 1, 2, 2, 3, 4, 2. All right. Hopefully your dot plot looks something like mine. Is this a sampling distribution? Tyler's saying no, and Tyler is right. It's not. We didn't take a sample. We actually looked at the population, right? The population is all AP Stat students in Block 3. I asked each of you how many siblings you had. So this is a population distribution. And I guess I'll put it down below, because otherwise I'm going to run into my line at 2s. And since it's a population distribution, we can find the true mean number of siblings for this class. Add all these together, divide by, it should still be 18, 3, 6, 9, 13, 15, 17, and me makes 18. And I want you to find the true mean and use the correct notation. Are you working with mu? Or are you working with X bar here? Alright. Are we using mu or x bar? We're using mu. Populations, that means you're working with the parameter, and parameters for means is mu. So we have mu equals, and what did you guys get for the average? If we round, it was 2.3 with a bunch of 8s and then a 9 at the end. So if we round, 2.39. All right, so now we're going to take a random sample of 4 students, and we're going to record the mean. I'm going to show you how to do it. Then I'm going to have you guys do it, and we're going to record everybody's sample of 4 students. Okay? Now, up here, we have everybody, the population, the number of siblings they have. To take a random sample, I'm going to use a random digit generator on my calculator to pick 4 of the numbers. I'm just going to label them 1 through 18. So just right below, I'm going to put the numbers 1, 2, 3, 4, 5, all the way to 18. That way, when my calculator gives me 4 numbers between 1 and 18, I know which number of siblings it corresponds to. And I gave Eric my calculator. So I want to take a random sample of 4 students. So I'm going to use my random digit generator to pick 4 for me. I'll give you one in just a minute. Remember, you're going to put the lowest number, highest number, and how many you want chosen. So we're going to do 1 to 18, and we want 4. We do not want repeats, so if it gives you repeats, you're going to ignore it. You hit math, go to prob, number 5, rand int. Newer ones will prompt you, otherwise you type them in with commas in between. So I got 17, 17, 3, 10, so I'm just going to redo it. And I get 8.
1, 1, 13, 13.
Redo it again. Until you get 4 separate numbers. So I got 8, 14, 1, and 7. So 8 was 2 siblings. 14 was also 2 siblings. 1 was also 2 siblings. And 7 was also 2 siblings. So that makes finding my average easy. 8 divided by 4 is 2. So you guys are going to find your sample of 4, record it where I just put mine, and then I'm going to go around and ask you what your sample was. And you need a calculator. Sorry. Anybody else need a calculator? No questions? What's up? No. So 4. Hayden, you need a calculator? Oh, really? What are your 4 random digits?
12, 4, 6.
Where'd you get them from?
My calculator.
Where's your calculator?
Oh, I put it back in my backpack.
Interesting.
It's just
Somebody spelled. All right. Let's see. I started with Eric once. Started with Tyler once. I gotta start with one of you guys again, so otherwise I'll get confused. So Tyler, what was the mean you got?
2.5.
Nate?
2.25.
Molly?
2.5.
And you guys obviously probably have figured out you want to write these down just like before. Jillian?
3.25.
Anna?
2.5.
Haley?
3.25.
Maddie? Cheyenne?
2.75.
Zach?
2.75.
Hannah?
2.75.
Michelle?
2.25.
Calvin? Amelia?
2.75.
Shelley?
1.75.
1. Thank you. Eric?
2.25.
Noah?
2.5.
And Hayden?
2.75.
And then you guys can add mine to it, which you saw I got 2. So now we're going to make a dot plot of our sampling distribution in that big wide open space. Lowest one was 1.75, highest 3.25. So I think I'll go 1 to 4, just to make numbers easy for myself. One, 4, that means 2 and 3. Oh my goodness. It's like a high-pitched humming from that video. Drives me insane. It's 1.5. I'm just gonna label the halves, but I do have the 3, like the 0.25 and the 0.75. And then if you guys will put your dots where they belong, please. And then we'll compare when we're done. See, doesn't it sound like they're having a dance party over there? There's no talking, it's just music. Alright, so hopefully your dot plot looks something like this. I'm going to label it, it's a sampling distribution. We're looking at X bar because we're looking at a sample. I know, right? Alright, so does our sampling distribution display bias? So do we overestimate or underestimate the true mean? So we found the true mean from our population is about 2.39 because we rounded a little. So we're going to find the center of our sampling distribution, 18 people, so 18 dots. So we're looking for the 9th and 10th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's these two. So this time we don't have to add them together and divide by 2. Our center is at 2.5. So, do we have bias? And if so, is it high or low?
It's high.
Why do you say high?
Well, not actually, no, it's more low, but the overestimated because like training
So we have bias because we overestimated the true mean. And then we are overestimating, and I think that's why you said high, and then you corrected yourself, and it's low because we're close to the true mean. So we would say we have low bias. We overestimated, so bias is present, but we didn't overestimate by too much, so it's low bias, if I could speak. Do we have high variability? Our range is actually pretty small, right? 3.25 to 1.75, that's what, 1.5?
Yeah.
Yeah, 1.5. So I would say it's actually pretty low variability. It's not a very big spread at all. So no. Because the question is, do we have high variability? No. Range is 3.25 minus 1.75, which is equal to 1.5. I've done this in some years, and we'll have like a range of like 5 on our sampling distribution, so we did pretty good. Is our dot plot a true sampling distribution? Did we take all possible samples of size 4? No. We took 18 of them, although some of you might have had repeats, because if you haven't used the random digit generator too much, they're actually written to start at a certain set of random digits, and so some of you might have actually gotten the same 4 random digits. Because we did not take all possible samples of size 4. Could we take all possible samples of size 4? Nobody wants to answer that one. Abby says no. I agree with you, Abby. I don't know the actual number. Sorry, I'm stealing this. Because it felt easier to walk over to you than get in the bag. We have 18. Sorry, just going back to what I've taught you before. If we do the combinatorics, it'll tell us how many samples the size 4 there are from 18 students. 3,060, so I mean, you probably could. Would you want to? No way. That's a lot of samples of size 4. So, in case I haven't put it in your head enough, here's the definition of a sampling distribution again. And I think for the second time this lesson, I promise I'll have a question about this on your test. A sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. And I shouldn't have put my asterisk before I wrote the word population. Sorry. A Y? Even when I don't write over it? A what?
A fly.
A fly.
Like a firefly. Just
Yeah.
a thought.
With the head down here and the wings and the tail. Yeah, I see it. Yeah. I heard a lot of papers turn, so I'm assuming we're all good. So, we talked about this at the end of class last time. What makes a statistic a good estimator of a parameter? Two things. What are they? Low bias. I don't know if he used the context clues, because low bias, and then I say high bias is usually because of a poor sampling method. And then Maddie hit the other one. We want low variability. And the best way to reduce our variability is to increase our sample size. Is it already that time?
Yes.
Go ahead. Oh, thank you. A tip. Aw, you give me a penny. Thanks, Calvin. All right, so down below, we're going to look at the 4 possibilities for a statistic. So high bias, high variability, high bias, low variability, low bias, high variability, and then the one we're aiming for, low bias with low variability. We're going to make sketches of dot plots. Are these actual sets of data? No. It's the dot plot and the shape that you're looking at that really matters. So sometimes it may look like I'm just throwing dots on there, which, hey, that's true. I'm just, well, I was going to say I'm making it up as I go, but I'm not. I drew them out beforehand so that I didn't accidentally mix them up. Because that would be embarrassing if I said one was one thing and then I drew the wrong picture. Alright, so we're estimating a proportion using a statistic, and we know the parameter is p equals 0.2. So high bias means that we're either going to overestimate or underestimate the actual parameter, and high variability means we have a lot of spread for our data. So if our parameter is 0.2, and we have, I'm going to use marker to make these dots show up more. We have our data nice and spread out. We have some down here, but then we have a lot up here. And let's say that up here we're at, I don't know, like 0.6. So you can see that our data center is more around 0.6 than 0.2. So we have high bias, we overestimated. And we have high variability because we have a large spread of data. So the next example is high bias, but with low variability. So here's our parameter, p equals 0.2. We have our data. So high bias, because let's say we're up at 0.6 again, we overestimate our parameter. Low variability, because all our data is really close together around that overestimation. low bias with high variability. So parameter is still 0.2. Low bias, so our center is going to be around the actual parameter. High variability means we're going to have a big spread of data. And then the goal is to have low bias and low variability. So we want it actually centered around our parameter, and we don't want it spread out too much. And then just a note down below, when you increase the sample size, it decreases variability, but it doesn't do anything to help you with your bias. Flip to the back side. We're going to look at this one together. So the histogram on the left, this one, shows the intervals in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median is 75? Sorry, yeah. 75 minutes. Fathom software, which is just a statistical software, was used to take 500 SRSs, simple random samples of size 10 from the population. The 500 values of the sample median are displayed in the histogram on the right. So we have our population distribution on the left. We have our sampling distribution on the right. The mean of the 500 sample median values is 73.5. So we might just want to make a quick note. This is our population distribution. And this is our sampling distribution. We're told the median is 75 minutes. So we tend to focus on means and proportions, but there are other statistics out there like the median, which we've talked about way back at the beginning of the year. So they will sometimes bring them up. I won't have you find like the median of a population or a sampling distribution. We focus on proportions and means. For a parameter median, we use capital M. So they tell us that the parameter is capital M equals 75 minutes. And then down here, they tell us that the 500 sample median values is 73.5. So our statistic, which for median we use little m, is 73.5. So we have our population distribution with our parameter. We have our sampling distribution with our statistic. So the first question says, is the sample median an unbiased estimator of the population median? Unbiased means that there is no bias at all. We would have to be completely the same with our parameter and our statistic. So we have our statistic is lower than our parameters, so we did underestimate, so we do have bias. Unbiased means no underestimation or overestimation at all. Let's see, I think I'll use green. So M is a biased estimator of M because it underestimated. Sorry. My writing is running into each other. That's why I use different colors though. So unbiased means no over or underestimation. Our sample median did underestimate, so it is a biased estimator of the parameter median. Any questions about that one? So then number 2 says, suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? Any thoughts on that one? We increase our sample size. Is our spread going to get bigger, smaller, or stay the same? Say that again. Smaller. If you want to reduce variability, which is a measure of spread, increase your sample size. So if we increase our sample size from 10 to 20, our spread is going to get smaller. I'm going to abbreviate increase. And I'm going to abbreviate decrease because I'm running out of time. Sorry. And then the last one says, describe the shape of the sampling distribution. Explain what this means in terms of overestimating or underestimating the population median. So, what shape does our sampling distribution have? The one on the right. Do we remember how to describe shape?
Sucks.
We're just doing the first S. It's unimodal. It's skewed which way? To the left. And if it's skewed left, what does that tell us?
Outlier.
That we probably have low outliers, which is going to make us have bias. I think it was Hannah who said it. Because bias is overestimating or underestimating. So if we're skewed left, we have outliers in the low end, which means that when we estimate our parameter, we're probably going to underestimate, which if we look back at number 1, we did underestimate the actual median. questions? It's okay, Zach.